Hello everyone, my name is Shitij Karnawat and I am going to present my review on the unsupervised learning of depth and ego motion from video. Humans are remarkably capable of inferring ego motion and the 3D structure of scene even over short time scales, whereas computer vision models have failed in most real-world scenarios due to occlusions, lack of texture, etc. Inspired from this, the authors try a first of its kind unsupervised learning approach to estimate both the depth and the camera pose from a given monocular video. The authors propose a framework for jointly training a single view depth CNN and a camera pose estimation CNN from unlabeled videos. Both of these CNNs can also be used separately during the test time. Using a novel view synthesis as the supervision signal, the authors synthesize a target view and predict its depth per pixel. While earlier works have explored this option for depth estimation and multi-view stereo, they require the camera pose during training and in some cases during testing too, whereas the author's technique do not require any data of such kind. The framework also predicts the pose as a part of the learning. The author assumes that the video scene is static and that there are no occlusions between the target and source views. The source views are transformed to the target view during the view synthesis step. Along with this, the authors also assume that the surface is Lambertian, so that the photo consistency error is meaningful. In any of these assumptions are violated in training, the gradients are corrupted. To make this frame robust, the, the training of an additional network called explanatory network has been added. The output of this network generates a mask which essentially helps in making the video sequence static and helps in masking out moving objects. For single view depth estimation, the authors use a DispNet-like architecture based on encoders and decoders with skip connections and multi-scale predictions. All convolutional layers are followed by a ReLU activation except the prediction layer, which uses a sigmoid function for its activation. For the pose estimation network, the input is the target view concatenated with the source views, and the output is the relative pose between the target and source view. It consists of 7 convolutional layers with ReLU as their activation, followed by a convolutional layer with 6 by n-1 output channels, which give us the 3 Euler angles and the 3D translation for each source image. All this is followed by a global average pooling. The explainability network shares the first 5 layers with the pose network, followed by 5 deconvolutional layers with multi-scale predictions. The authors evaluate the paper on the Kitty dataset and the Make 3D dataset. Using Kitty, they evaluate the depth and pose predictions, while the Make 3D dataset is used for evaluating the generalization capabilities of the network. The images in the video are resized to 128 by 416 pixels during training, even though the depth and pose networks can handle any size of images. The results of the experiment show that the proposed network outperforms all existing methods, including supervised methods that use ground truth for training. These are some of the results that the authors have provided in their paper. This paper is one of the first approaches to use unsupervised learning for depth and pose estimation. As most methods require either the depth or the pose information to predict the other, this paper presents a novel way to predict both the depth and pose information from monocular videos without depending on either of them. As seen from the experiments performed, the proposed framework outperforms existing techniques in both depth estimation and pose prediction, even when compared to supervised techniques. The network can also generalize efficiently, as seen from the results when tested directly on the Make 3D dataset, using Cityscape and Kitty as training data. Some cons that I found while reading this paper is that the framework is heavily dependent on the prior assumptions made. If any of these assumptions are violated, the gradient can be corrupted and potentially inhibit the training of the framework. The proposed method cannot handle any occlusions between the target and source views. It cannot handle any kind of motion in the video and requires masking of data if any motion is detected, which leads to loss of information, leading into loss of edges, which in turn leads to loss in depth information. It is also assumed that the camera intrinsics are known, which limits the use of internet videos. Along with this, the predictions only give us a 2.5D depth map, which could be used to train a 3D volumetric representation. Some future improvements on the work in this paper that can be predicting the depth and pose, even if there are dynamic objects in the video sequence. Predicting both the factors, even with occlusions, is another feature that needs to be worked on. The framework can be extended to generate full 3D volumetric representations instead of 2.5D depth maps. The framework can also make use of segmentation to improve and handle dynamic objects. The dependency on the camera uh, intrinsics forbid the use of videos obtained from the internet. This needs to be addressed and worked on as many videos lack such information. Thank you.